and welcome to the SimScale webinar. My name is Dr. Nagman Khan. I'm delighted to welcome you here today from the SimScale marketing team to join us on this event called AI-powered valve design and optimization. I'm joined today by my colleague, Ajit Kumar, Senior Application Engineer here at SimScale. I'm going to very quickly hand over to Ajit to run the main presentation and live demonstration, and then I'll be back at the end where we'll take some Q&A from the attendees. So please remember to post your questions using the questions panel in the GoToWebinar pop-up, and we'll try and get through as many as we can at the end. Okay, we're also happy to share a copy of the recording for this webinar. Give us a few days just to process the video, tidy it up a bit, and we can share that with you later this week or early next week. So I'm going to hand over to Ajit. And Ajit, personally speaking, this is a topic of great interest, not just valves and flow control, but also the combination of PDE and AI features in SimScale. So we've worked hard, you and the team have worked hard to put this demo and feature set together, and we're looking forward to see what you're about to present. Ajit.
Definitely. Thanks a lot, Nagman, for the brief introduction, and a warm welcome from my side as well to the audience present here. I am Ajit. I work as a senior solutions engineer here at SimScale. Have a background in computational mechanics, so anything related to fluid dynamics, structural dynamics, and this is my expertise. And in today's webinar, as Nagman mentioned, this is a combination of quite a lot of things that you can do with SimScale, you can do with simulations in general, and how you can use AI to actually power your design and optimization. Yeah, let's get into that now. And here is a quick list of topics that we are going to cover in today's session. It involves a quick introduction to SimScale for those who are new to SimScale, and we will also look into how SimScale integrates AI for simulations in general, and we'll also jump into a specific case study that we're going to see on a valve and how we can actually use AI to optimize or actually predict results for the valve using AI. We'll do the demo on the platform so you can see how SimScale works in real time and how we can access the cloud native simulation platform and make use of these simulations for your design study. And finally, we also look into some results and where these AI predictions can be used later down the line as well. So that's a step back from what we hear all around in the market. AI is a buzz, but in this presentation, I would like to quickly cover on where these AI can be used in terms of simulation as well. So that's going to be interesting. And we also have a few minutes for the question and answer section. So as Nagman mentioned, if you have any questions, you put that into the question section right away, and we're happy to answer them at the end of the session. Yeah. Let's get into the presentation and see who SimScale are and what we actually do in the market. SimScale is a cloud-native simulation tool that helps engineering organizations to innovate faster. And when comparing to other traditional CFD tools or FEA tools or other CAE tools present in the market, how do we do it? We actually do it by making high-fidelity engineering simulations truly accessible and also at any scale. And the moment you hear about cloud, that combines the advantages that it brings by scaling up the number of simulations or running parallel simulations. And this is one of the high point of SimScale when compared to the traditional tools. Don't listen to us, but you can also see there's a lot of customers using SimScale in their day-to-day process, design process, simulation process, where you can see some of the examples where ITW uses it for product performance using FEA capabilities within SimScale, and Bueller is using SimScale for food industry, optimizing their products in terms of efficiency and performance. And there are other ample amount of examples from our customers that you can go through. And a list of customers, sorted out customers here at the bottom of the screen as well. Yeah, that's about SimScale. And SimScale was founded in 2012 by 5 graduates from the TU Munich in Germany. And one of the vision was to actually make simulation accessible to all engineers rather than only to experts in the simulation field. And you can see how we do that in the next slide, where you can see the first thing you notice when you talk about SimScale is we are cloud native. So you don't need any VPN. There's no need for remote desktop connections or any access from local hardware. Everything is done on the cloud within a browser. All you need is a stable internet connection, and you can open up SimScale on a browser and start simulating. The next thing that stands out is we have a platform that gives users the ability to run a broad physics, including fluid dynamics, thermodynamics, and also structural simulations, all under the same hood. So you can actually run all of them if you access into SimScale within a browser directly. The other thing that stands out, and we're proud to say that we are supporting our customers in a unique way because we're on cloud. You can actually get access to our simulation experts by simply clicking the live platform chat and ask us questions and have a real-time collaboration with our support team as well. This works the other way as well. If you have a team of engineers working on SimScale on a product, they can also share the projects between them and collaborate on real time. And when it comes to the cloud computing, you definitely have the advantage of running multiple simulations at the same time. For example, for a pump or a valve case study, you would need to actually do a full performance curve or a pump curve. In that case, you don't need to wait for one operating point to finish to start a new one, but you can start all of the operating conditions at the same time, and they are going to run in parallel on a separate instance for you using the cloud platform. And the topic for today is the AI-powered valve design and optimization. And SimScale integrates AI within its platform without any third-party module or hood that you need to jump between to actually use the data that you create out of CFD. And we do that using an integrated solution, which we'll look into in detail later down. Great. What does SimScale or what does AI bring to CFD or simulation domain, right? We want to quickly look at how this can work out and how we actually do it and what are the few advantages of using AI prediction for simulations. In this case, you can see we have taken a valve case, and to start with, you need the simulation data, right? All the AI algorithms are trained on existing data or new data that you can create. So if you have the simulation data, they are ready to be trained with an AI model within SimScale because you don't need to jump between different tools to collect the data, pre-process it, and make it ready for the AI tool to actually read it. Everything is included and integrated within SimScale. And once when you have this simulation data, you can easily train the AI model and then start predicting the results in real time. Suppose if you have a valve case that runs within a few minutes or let's say 30 minutes or an hour, then you have a bunch of simulations that you can base the AI prediction with. Then you can start predicting the results within a few seconds. So the main thing to note here is if you have the simulation data, you can start predicting the results within a few seconds. That cuts down the runtime, the effort, and all the included activities in the background to actually get the results finally. That's just a quick overview of the AI models. But the other part that comes with SimScale is that since you're already on a simulation tool, once when you predict AI, if you want to validate or verify the results that you are predicting, you can simply switch between the partial differential equation based models or the actual simulation and run a simulation as well in parallel. So that's one advantage that you can also see in terms of verification of your models. I'll give a pause here and again remind all the audience to actually ask your questions in the question section, and we'll be happy to answer them at the end of this session. Let's jump into the main study for today. So it's a valve case, it's a globe valve where we have different operating conditions that you want to try. And with respect to the prediction, we are going to use a design space of different parameters. geometrically and operating conditions wise as well. That is explained here, where you can see we're trying to actually build a database where we want to find out the flow characteristics like pressure and the forces on the valve for different valve positions. For example, here you can see we have the geometry variations that ranges from 2 millimeters to 24 millimeters on the valve position. And we have a supply rate of 0.02 kilograms per second to up to 0.5 kilogram per second. That's going to be applied for each of the valve position here. So in total, we have a database of about 117 design samples that we're going to run and use that for the prediction of flow characteristics later using the AI. Yeah. In general, there are a few numbers here on the screen, but we can talk about that later. So the training took about within 7 hours to actually get the data, process it everything on an on-demand GPU, and then give you back the AI model so that users can use that for prediction. Great. That's about the case that we're going to discuss, but usually simulations are a bit boring, right? So let's make it a little bit interesting by introducing two more characters into the play here. So we have two engineers. On the top, you can see, you can name him as Tom. I like Tom and Jerry, so I'm going to name him as Tom. And on the bottom, we have Jerry. And Tom is a structural engineer or a structural expert working in a valve industry. And he's been assigned with a task that to analyze the valve for different flow conditions and then see if the forces and the pressure values that he can get from the flow field can actually be applied for the valve design he's going to actually iterate on, right? That is his task. And something to note here is Tom has several years of structural analysis expertise, but the last time he ran CFD was in his university. So he's not that familiar with the CFD, and he would still like to use the data from a CFD-driven simulation to make sure his product is actually going to increase in performance. On the bottom, we have Jerry, who is a process or a systems engineer who also has expertise in reduced order models and system level designing. So her task is to actually collect the data from the simulations and plug it into a system level a design here. For example, you can imagine that we have like a process plant where there are multiple valves involved and a lot of other components involved. And right now we are trying to actually troubleshoot what will happen if the valve goes over range or at different valve positions, what's going to be the effect on the entire system. That's her task. And to help these two engineers, we're going to use SimScale's integrated AI tool and see how they can actually make use of simulation results for their data-driven design. Yeah. At this point, I'll quickly jump onto the platform and show you how you can work with SimScale with respect to Tom and Jerry here. Yeah. Great. Then let me jump back to SimScale. And the moment you talk about SimScale, as I mentioned already, it's completely on a browser. To access SimScale, all you need to do is go into simscale.com on a browser and then log in with your credentials. Once when you log in, this is where you end up, where you can see all your projects that's been created by you or shared by someone else from the team as well. In this case, I have a folder named Valve AI, and I also have certain templates that I can start using as well. Let's imagine we put on Tom's hat and Tom comes in. He wants to actually do a valve simulation, which is a CFD simulation. As an intern, he wants to pick up the results and use it in a structural simulation, right? That's going to be his task. So to do that, we create a new project and name that as, let's say, valve analysis. And any project that you create within your account is private to you unless you share it with our support or one of your colleagues by entering their email ID. The moment you create the project, SimScale will opt for geometry input. But as Tom is not that familiar with the CFD workflow, he doesn't know where to start, right? This is just a scenario that happens for many of the engineers on different tools on where to start the simulation, right? To address that, SimScale actually has a templater approach where a new user can actually jump in, and instead of starting from scratch, they can actually pick up one of the existing template and start working on that as well. And we're going to see how the workflow looks like for Tom here. So instead of importing a geometry, I'm going to import a template, a simulation template from the existing report. So I'm going to import a simulation. And if I look into my folders, I can already see I already have a valve template, right? This valve template can be built with the support of SimScale team, or one of the experts in the company itself can control the template that can be shared with all the users. So right now, this template has been built by an expert, is shared to Tom for him to actually start using the CFD solutions. So I'm going to pick up one of the template, let's say the 18 millimeter opening of the valve. And when I import the simulation, I already have the respective geometry used in the simulation. And on top of that, I also have all the simulation settings done for me already from the template. At this point, all I need to do is verify if I'm using the right boundary conditions. For example, I know that I want to actually test the valve for zero 0.1 kilograms per second. So I'm going to enter that value here. And the moment you have your simulation template ready, you don't need to actually do the actual simulation. You can use the existing AI model to start predicting the values directly. And this is done by selecting the AI model that is respective for this valve. So in this case, I'm going to go with Globe Valve version 2. And within a few seconds, I'm going to get the results of the valve in terms of pressure and velocity as well. I'll give a few seconds for the results to load. And as I mentioned, the way we support our customers is also unique. And let's say if you have a template and you want to actually change something which you didn't know how to set up, right? You can directly open up the chat at the bottom right corner, send us a message stating, hey, I'm using this template and I don't know how to change this particular parameter. Then we are happy to jump in, help you then and there, where you can also share your project and we can take a look at the template and give you back our best practice guidelines as well. That's how the support works. And meanwhile, you can already see on the screen, we have the results already predicted using the AI model. So I can go back, I can start integrating the results. For example, I can range out the velocity and then see how the flow looks like. The flow comes in from this direction and then it goes through this valve. And the valve head is at 18 mm from the flow direction. So you can see there's a high velocity region on here. And if I hide this face, you can see clearly there are a few recirculation zones predicted as well. On the right, you have the main parameters that you get out of such a prediction. And that includes the forces on the valve. So you can define where you want to write out the forces already in the template, and the AI prediction will give you the values directly as a quantity here that can be copied and used further down the line. For example, we have the total force in X, Y, and Z directions. In addition to that, we also have the pressure drop according to the flow rate that we give here. For example, if you want to change the flow rate and see, let's say I want to use a different flow rate and I want to predict the results. All you need to do is change the boundary conditions and wait a few seconds for the new results to be predicted using the AI model. So let's wait for a few seconds, and then taking a step back, Tom has to actually do some design modifications to the valve as well, right? He wants to actually check the valve at positions different than 18 millimeters as well, right? So we can focus on that quickly. So now you can see the second prediction is already there with a different flow rate without any simulation run on your template. When you talk about AI, there is an important question you need to address, right? So how can I actually believe the results that AI can give? So in order to address that, you can quickly verify what is predicted here is corresponding to what you have in your simulations. So let me go back to one of the existing trained data. So I'm going to go with 0.1 kilogram per second. And I'm going to bring up my actual CFD simulation as well. So let me quickly get the project. And here you can see on the left, we have the training data on which the AI model is trained. So this is the design space for the CFD database, right? So on the right, we have the AI prediction already written. So in this case, let's open up the 18 millimeter model and run down to the flow rate that matches our predicted results. So here we have the 0.1 kilogram per second. Let's go into that and post-process and see whether the prediction is good enough for me to actually make design decisions on that. So the results have been loaded now. On the left, you have the CFD simulations. On the right, we have the AI prediction here. So on a general scale, you can see the flow fields look pretty much closer, right? We have already also have these recirculation zones predicted and also the accelerations on the other side of the valve because of the flow rate. There's also a bit of flow separation happening here that is also predicted here, and a bit of acceleration here at the bottom as well. So in general, this is how you can verify if your prediction is good enough. And if you're confident using that, then you can start using the prediction AI predicted results for your design iterations to be made. Right? This is the verification stage that you can do. But as you can see, you're not limited to the flow rates that have been trained. You can also go on a random flow rate within the range and start predicting the results. So I'm going to go back to my prediction here. And now I can actually, now that I'm confident, I can go ahead and try a different flow rate as well. And on the right, you can see there was a confidence meter. That gives you a good indication of how close the AI results are to the trained CFD actual data, right? This will give you a good insight on the first check on how good the results are. And on top, if you find that this percentage goes down because you're using some value out of the range, which is not used for the training, or the geometry is completely different. For example, you're using a valve model, valve AI model for a pump, for example, then the AI doesn't know how to handle that, so the confidence levels go down. In that case, you can go back to your experts or contact SimScale and say that, hey, my AI prediction is not good enough for me to use. So what can we do? In that case, you can run more simulations or try to actually add more to your design space and retrain your AI model directly within SimScale. This will help you improve the AI prediction as you go. Yep. Great. Now we have seen a quick verification of CFD versus AI. And now we want to use the AI prediction for a different model or a geometric variation, right? I'm going to close the AI prediction here. And now I can try to import a different geometry. So I'm going to go back to my template folder and say, I want a new geometry which has 3 mm opening, which is not part of the AI training database. So this is a completely new geometry that I want to actually see how the performance look like, right? So I have my 3 mm model. Let me quickly check if I have the geometry. Okay, it seems like it's a 7.5 mm opening of the valve, so shouldn't be bad. Let's go with a 7.5 degree opening of the valve. And now I have all my boundary conditions already imported, and I can directly go ahead and use the AI prediction to see a completely new model on how it behaves in terms of flows and the pressure values. Yeah. While the simulation is, the AI prediction is running, Tom had to actually do a structural simulation as well based on the AI prediction or the results from the flow analysis, right? So now you can see it's a new model. We have about 86% of confidence. So it's good enough for me to make design decisions. So I can go ahead and say, hey, I have a pressure drop of certain value and the forces on the valves are of certain value. I can quickly copy that and use that in a structural simulation, right? Again, I'm going to import a simulation, a structural simulation this time, and import the values that I predicted from the CFD run. So I'm going to go with a flange structural simulation. And now with the setup that I have, I can go back to my internal pressure, simply change whatever I have predicted here and say I have a 15 bar pressure internally, and I can start a new structural simulation based on the results. The advantage is that you have both the AI prediction and this high fidelity simulation accessible under the same hood. And this can help users to actually switch between them depending upon your requirements. So I can predict a CFD simulation, but I can run an actual FEA simulation in the same project and get the required results at the same time. And that ends the task of Tom. Now he can actually wait for a few minutes and then take a look at the FEA results and see if his valve actually performs better in terms of the flow pressure and how does it actually handle in terms of structural integrity as well. Great. This is just a quick example, but as I mentioned, this is not explicitly or specifically for valves. You can also have a pump case or a different product that can be trained with AI and start predicting results within a few seconds. Great. I hope this gave you a quick introduction on how you can use AI model in predicting the results and how you can use them for a different analysis as well. But the second use case is that we have Jerry, who is a system level design engineer, who wants to use simulation results in a process control or a system level analysis, right? For that, SimScale also provides this AI prediction capabilities using the API, the application interface, where the users doesn't even need to actually use the GUI, but actually have a simple Python script where they can actually start predicting and copying the data that you predict into a system level design. That way, the system engineer who doesn't have any experience with simulation or 3D simulations in general can even use a completely built template, extract the results, use them in a system level design. And that's what you have seen here, right? So now Jerry also has the predicted results within a few seconds. This is really important because for a process or a control engineering, you would like to actually change the variables or the parameters to see how the system behaves in a continuous manner. And Jerry can now get results within a few seconds, plug it into her system model and see how the system behaves. So these are two sample cases where the predicted results can be used. And there are multiple other use cases that we can discuss. If you have anything specific that you want to try, let us know. We are happy to actually talk with you in person as well and try to understand how you can use these kind of predictions in your design process. Great. That wraps up quickly what you can do with the AI prediction. And I already saw one question on whether you have examples of other cases. Maybe I can answer that already and then jump back to the question and answer section and do a quick summary as well. So as we mentioned, this is not specific for valves. So if I go back to my full screen, you can see we have cases where we ran a pump model with different geometric variations, including number of blades or blade thickness or blade angles. And in total, we ran about 180 variants that took about 2 hours because we're running everything in parallel on SimScale. And there's no pre-processing time for the data to be trained for an AI model. So within a few hours, you can actually get the AI prediction ready, which can be used by your engineers to actually make design informed decisions directly. We've also seen from our customers that some use this AI prediction for marketing and sales, or if you're on a client site and you want to actually present something that you have designed and get their confirmation, instead of running the actual simulation that might take hours, you can directly use the AI prediction and show them the results and get the confirmation, and then come back and run a CFD verification if required within the same platform. There are other examples where we have done the muffler study, where we had about 200 different data samples run within 2 hours, and then again used in AI prediction. And also on the structural side, you can also do this not just with flow, parameters, you can do a structural simulation and also start predicting the structural integrity or the stresses in your components or your assemblies as well. Great. I think this would have given a good overview of where the AI prediction can be used and how this can be used. We're open for questions. And just before getting into the question, before handing over to Nagman, I wanted to quickly summarize this. So also want to compare how the traditional approach might actually take this AI prediction. So on the left, you see if you want to use the AI prediction in simulations, you would need to first of all collect the data and the simulation runs that you would need to base this prediction on. That may be from tool A or B or C. You need to actually pre-process them. That needs a separate hardware and programming to actually collect the data and make it ready for the AI model to actually read in. And you also need specific hardware to actually run the AI training model as well. Once when that is done, if you find that one of the simulation is not performing well or there's an anomaly in your CFD data, you would need to trace back who ran the simulation, on which tool they have used to run the simulation. So all these challenges will might actually block you in case if you have a siloed approach, right? But with SimScale, you can avoid them because you have already the simulation data in the same account, which doesn't need any pre-processing or less pre-processing because we have the simulation data with the inputs and the results available for the users. The user can actually train the data from their SimScale account directly and start predicting. And in case, as we mentioned, if you want to verify, you can directly switch between an AI solver to a partial differential equation solver and verify that within the same platform itself. That wraps up a quick overview of the AI prediction and how this can be used specifically for valve application here, but for other cases as well. But I'll hand it over to Nagman to actually see if you have any questions from the audience.
Ajit, hi, can you hear me?
Yes, Nagman.
Excellent. Thanks so much, Ajit, for that Valve demo. That was fantastic. Really great. I like the story, the narrative around, Tom and Jerry and different use cases and user personas of that. We do have a couple of questions. We have time for a couple of quick questions. Ajit, the valve case and the pump case you showed were both CFD, yeah? And then at the end, you briefly showed the bellow and FEA case. So in general, what are the different types of physics where the AI features are enabled in SimScale that attendees and users can try out?
Yeah, that's a good question. So yeah, for this case, we used two of the fluid dynamic simulations, but in general, all the analysis type that is available within SimScale can be trained with AI. So it includes the simple incompressible or compressible flow. So you can imagine the components or the products that you can test. You can also jump to the structural side of things, or you can also run thermodynamic simulations like battery thermal pack, for example, and all those analysis type can also be trained with AI to start predicting. I hope that answers the
Okay.
question. Yeah.
Yeah, absolutely interesting. And you briefly covered this, but how much data is actually needed, right, to train the model before you can reasonably expect a high confidence in the AI predictions? So before you get to the predictions, the bit before that, what's your experience of that? Is there a rule of thumb based on, the application, the use case, the complexity of the CAD model?
Mhm. That's again a really valid question, I would say. We get this question a lot from the customers who are starting to use AI as well, right? So as we all know, AI is based on the data that we provide. And if the data is good enough, you get a good confidence in prediction. And what we have seen from our customer case studies and a few other demo projects is to have at least 7 to 8 different operating conditions for each of the geometric variations that you do. And this again depends on the cases. Your case might be simpler than this or complex than this. So as a rule of thumb, I would say 7 to 8 simulations compare geometrical variations will already give you high level of confidence, like about 90%, as we have seen in our cases. And if you want to improve that fidelity a little bit more, you can always train the AI model in a next version, including more simulations in the background. So you can have 117 design samples for this case. But if you find out that, hey, my flow rate is way over what I have used, you can train that with 10 more simulations. And in total, you can train with 127 simulations, and you can start getting good
Yeah.
predictions on your new ranges. Yeah.
Interesting. And the example you showed had quite a high level of confidence, right? We have
Yes.
an attendee asking, at which level of confidence would you say don't use the AI predictions? You know, what percentage does it have to be? Or flip it around the other way, right?
Mhm.
What's the minimum confidence level you should have before you base some early stage design decisions on the AI results?
Yeah. Um, I think that's an expert level question, right? So it depends upon the application. If you are in an early stage design a process where you don't have anything to base your design iterations on, I think even 85% or 80% is good enough to guide you through the right direction in design iterations, right? That's one scenario where you can imagine. But if you're in the final stage of your product, you want to use the AI prediction to make a few final changes or minimal changes, I would say um, over 95 or 90 percentage is a good number to start with. If you're not still convinced, you can actually run more simulations, train it, and have a good database so that you can start
Yeah,
predicting above
yeah.
95. Yeah.
Okay, fantastic. Let's take two more quick questions, Ajit.
Mhm.
So the next question is, how reliable is the AI model for extrapolating outside the trained range of parameters? And would you even recommend this at this stage?
Mhm. That's again a good question. We typically tend to suggest people to have the range of the design sample within which you want to predict. That's going to give you ideally good prediction. But if you want to go beyond the range that you have used in your design samples, it needs to be minimal, right? For example, for this case, we actually trained from 2 millimeter to 18 millimeter. And if I predict it for 20 millimeter, I will still get valid results, but the confidence level will be around 80, for example. It might even go uh, below that if you make a drastic change to the model or the flow conditions. So good rule of thumb, try to actually choose the design space wisely before you start the prediction. And if you have one or two cases that you want to predict with AI out of the range, it should be within, let's say, not more than 5% of change in the parameter or the flow conditions.
I see. Interesting. Okay, that's great. Okay, let's take the last two questions together. They're related. So,
Mhm.
Ajit, this all looks fantastic. How does a SimScale user get started with training their data? Can they do it themselves on their account? Is it a self-service feature now? And also for non-SimScale users, people looking to get started with SimScale, how would you suggest they get started? And after this, Ajit, I'll hand back to you for some closing remarks. Thank you.
Yeah, definitely. Thanks, Angwin. That's again a good question. So to get started with SimScale, it's as easy as that. Just go into a browser, type in simscale.com where you have your own account created. The login doesn't take more than 2 minutes. Once when you have your login, you can end up within the dashboard and you can directly start creating a project, right? The moment you have used SimScale, you want to actually use it for AI training. Every user have the capability to run their own models depending upon the type of offering that you have. And this can be done within SimScale directly. So at training.simscale.com, you can actually select the projects that you want to train and then use it for your prediction directly. So this can be done under each user. It doesn't have to be like a specific user or admin who needs to run the training. Great. I hope that answers the questions. I think we are almost at the time, and I would like to thank you all again for attending the webinar. I know that this is a quick overview of how you can use the AI data, how you can use an integrated AI cloud native simulation tool for these analysis. But if you have some examples, or if you have a project that needs quick prediction on a control level or on a system level or on different requirements, feel free to actually contact us. You can contact us or reach out to us at sales@simscale.com, and you should be able to get in touch with one of our SimScale experts or engineers, where we can sit one-to-one and discuss about your project in detail as well. I hope that's give you a good overview again, and I wish you a happy evening or afternoon from where you have joined, and we'll see you in the next one. Thank you.